Hi, my name is Isamar, and I'll be presenting this paper on modeling PFAS fate in transport in groundwater with and without precursor transformation. This was written by Michael et al. All right, so a little overview on PFAS. PFAS stands for per and polyfluoroalkyl substances. Um, these were developed around in 1930, but they've recently just become like a new emerging contaminant. PFAS has many uses, such as for water and oil repellents, which are used in like pots and pans that create a non-stick surface. We can also find them in our furniture and food wrapping. There's just a variety of uses for them. There are thousands of PFAS chemicals. PFAS isn't just one, but there's thousands of them. And the major ones that we come across are PFOA and PFOS, or PFOA and PFOS. And specifically in this article, we'll go over PFOA. It stands for perfluorooctanoic acid, and these are both long-chain PFAS. The objective of this study was to use numerical modeling to model the fate and transport plumes of PFOA within the saturated zone in groundwater. The two different scenarios used in the article for modeling were for scenario 1 was to use a precursor source. This means that there is a compound that participates or produces PFOA as a result of the source being metabolized or broken down. Within the second scenario, they modeled a plume with only PFOA as the source. And only the first scenario takes transformation into consideration when going to PFOA. The transformation of PFOA was not modeled in this study. This means that they did not look into the breakdown of PFOA in either scenario. This study wants to look at the effects of the precursors on the plume's residence time and whether they could extend its duration by decades. The tools used to model the fate and transport was ModFlow and MT3D. They modeled an aquifer which was mostly composed of silty sand, clean sand, and gravel. For this model, the dimensions of the aquifer were approximately 1,200 meters by 600 meters wide, and the thickness of this was approximately 15 meters. In the model, they had about 500,000 cells. Here we have the hydraulic conductivity values that they each for each cell. They used a software called GSLIB, which was used to come up with the K values in the X, Y, and Z directions. As for the specified heads, the upstream elevation was 15 meters and the downstream was 12 meters, which gave them approximately 0.0025 hydraulic gradient. And a steady state was assumed for the flow going in that X direction that was shown in the previous slide. To model the fate and transport, they used the values in table 1. This used a simplified assumption of a linear equilibrium absorption-desorption to avoid complicated chemical interactions between air, soil, and water. And they also have the dispersivity and diffusion coefficients, which also help model how far downstream the plumes go and how wide they get. For the two scenarios, they use different concentrations for the precursor in PFOA sources. Scenario 1 with the precursor used a higher concentration since it involves a transformation to PFOA. And the PFOA concentration after transformation should be around in the hundreds nanogram per liter. They made sure the concentrations were close to what were observed in the field. Overall, the PFOA total mass for both scenarios should be the same after the 25 years of exposure within this the boundaries. And after the 25 years, they modeled, they ran models for the next 50 years to predict the plume transport and for the remediation. This graph here shows the map of the aerial view of the source loading for scenario 1 precursor, which could be any type of hypothetical source. This one here, it could be either like a PFAS storage or a fire training area that uses a certain type of foam. And so for the first 25 years, the precursor is loading or leaching into the groundwater. And then in the next 25 years, or at year 50, where remediation starts taking place. And here in the model, it predicts that the precursor plume is still around to contribute PFOA transformation. And by the year 75, it is no longer present as a source. Here for model results for scenario 1, after 25 years, the precursor source is still attached to the plume, and PFOA is still loading or leaching into the groundwater. The max concentration right under the source location is about 772 nanograms per liter, and this plume extends about 18 meters from the source, and it goes in the direction of the flow, and it reaches about 2.4 meters depth below the water table. After after 50 years, the max concentration is about 9.3 nanograms per liter and extends over 1,100 meters. As for the depth, it's starting to reach the limit of what the model was set, which is approximately 15 meters. Here, after 75 years, the source is no longer attached to the plume, but remediation is still continuing. Here, the max concentration is less than 5 nanograms per liter, and the plume is still over 1,100 meters away beyond the model boundaries. As for scenario 2, with the source of PFOA only, after 25 years of loading and leaching into the groundwater, the plume reaches about a distance about 880 meters from the source point. And this distance is much more higher than in scenario 1 because the PFOA is being transformed and it takes time to get into the to be transformed. After the 50 years, the PFOA only source is no longer contributing to the leaching, and the max concentration is less than 1 nanogram per liter throughout this plume. And the plume is now over 1,100 meters distance from the source location, which is also beyond the boundary limits. 75 years, the plume is much smaller and has very small concentration. This article, I would say the reading difficulty would be at a medium, as it could get difficult understanding the chemistry of the fate and transport parameters, such as the partition coefficients and the absorption distribution coefficients. That would be the KOC and KD values. It could get difficult because every PFAS chemical would have its own set values or ranges that would have to be modeled. So a model might be limited to only modeling one type of contaminant at a time. And also for the diffusion and dispersivity coefficients, they also play an important role in the the transport of the contaminant once it's in the groundwater. As for the results, I agree with the results of both scenarios. Scenario 1 with the precursor that showed the longer plumes in higher concentrations even after 75 years of exposure and remediation. That would be like a result from the precursor source still being connected to the plume, which increases its size, time, and concentration. As for knowledge gaps, I would say that there is a need for more research on the precursor parameters in regards to transformation. Because PFAS is very complex, there needs to be more research of PFAS interactions in the Vadose zone between air, soil, and water. I believe in this article, they only considered the interaction in the saturated zone because that's where they have more research done compared to the Vadose. And I believe that, like, the next steps in modeling would be to include the transformation of PFOA. So in scenario 1, it goes from precursor to PFOA, and so the next step would be PFOA to the new contaminant, which could possibly be like a short chain PFAS or something completely different depending on the remediation that is taking place. Overall, the update of models is needed when parameters are better defined for specific PFAS chemicals. And it's possible that there might be even more PFAS chemicals in production, which might need to also be taken into consideration. And that's all I have, and thanks for watching.